In this video, you will see a focus on abstraction. As a teacher, you will naturally bring together many computational thinking strategies in your lessons. Once students are familiar with naming each of the computational thinking strategies, we encourage you to look for opportunities to bring them together. For example, in this video, there are also opportunities to identify debugging.
Put on your math heads, because we are going to do a new math focus.
Okay.
So this is on your sheet. Your sheets match this. The math focus here is to represent three-dimensional figures. Your paper is 2D. When you stack them all up, then it's 3D. Is the tissue box 2D or 3D? 3D. So we're going to represent those using nets. Remember, we did this before, I think maybe when you built your gingerbread houses. Remember when you take something and you break it down and unfold it, that's the net? We're going to use the nets to find surface area of these figures. So there are two things that we are going to do, two actions. And the first one, what does it mean to represent? You need to show something. And then the next thing we need to do is to
Find the surface area.
find the surface area. So that is our job. Have you ever had to find surface area at home for anything?
No, maybe.
No, not
At the beach.
At the beach. How did you find it at the beach?
Because there's no surface in the water.
Oh, surf. Okay, so that's, I'm glad you said that. Surf is a different word. It's not part of surface, but that's interesting. But if we think of this part, take out the word part, surf. What do you see there? Face. How many faces does a cube have?
Four.
What about the top and the bottom?
Two. No,
So altogether it has 6.
Wow.
So when we're talking faces, we're talking surface area. That's what we're talking about. We're talking about measuring all of those faces, the area of each face. Oh, we're so glad we have abstraction here. So, abstraction. So when you identify, what are you going to do? Show it, point it out. When you represent it, you already said that you are showing the important information in a problem or a situation. The last time we worked on something, we had a story and the people in the story were running. Did that turn out to be important information in the story?
Not at all.
No.
Not at all. So a lot of times students can do math in real life, but then when they read it on a school assignment, they say, oh, this is really confusing, because sometimes they don't know what to take out. And that's really important. What you leave in is important, but what you take out is important too. And abstraction helps us do that. I started asking you about what we were going to do, and you said we're going to represent and find the surface area. That's part of abstraction. So if you could read off your bookmark, somebody, the first bubble tells you what you're going to say in your head. Alianise?
What is this problem asking me to do?
One more time, louder.
What is this problem asking me to do?
Good. You can't do anything if you don't know what it is that you have to do. Then, we know we're using something there. What is the next bubble? Go ahead, Ruby Serna.
What information should I focus on?
Yeah. Should we focus on what's in the box?
Not at all.
Maybe, maybe not. What is the last bubble that you're going to really say in your head? Go with Yanalise first, and then I'll get you in the next question, Jaking.
Can I use a diagram or picture to show the important information?
And I have to admit, I love using diagrams and pictures, right? So we do this all the time. Right. I don't always stop and say it's abstraction, but we make models a lot, don't we? Anytime we make those arrows or those lists or those connections, that is finding ways to make diagrams. In your brain pop, you do that with those word maps. So ready? So imagine that these pictures are of cardboard boxes that, when did we open up the boxes and flatten them out like that? When is the time we do that? Almost every day. What did you say?
When we recycle.
Right, when we recycle, we open these up. So you might just think of it that way to make a connection. When they're folded up together to be 3D, we call those prisms. And we're going to imagine that they're packed with 1 centimeter cubes. We have cubes. I don't think we need to put them in right now, but I think we can imagine that, right? I happen to have a little Monopoly house that I found on the floor. And so this is an example about 1 centimeter.
Wow.
Right. Okay. Your box pictures are a little small, so we might want to look on the screen. You're definitely going to need to do some math in the side because the pictures are so small. So what are we using as a measurement unit? What does it say? All lengths are in centimeters. So you notice it only has numbers here. It doesn't tell you 3 watts, but are these going to be 3 feet?
No.
3 meters?
No.
3 what?
Centimeters.
3 centimeters. All right, I think we see everything. What? Just real quick to see how you're imagining things. Which one of those nets, if you fold it up to make a prism, is going to be the flattest one?
B.
Ooh, let's check.
B.
Okay, we'll talk about that later. I just wanted to see what you were thinking.
B.
Like almost put a long pizza in there, huh? So this is a bigger model that we can go back to. You have that on page 3. On page 4, it asks you to compare the surface area of the boxes. So with this, we need to know how to do surface area, don't we? Do you remember area at all?
Yes.
Area code.
Not an area code, an area like a way to figure it out. If I have one face and it's like this, and I want to find the area, what 2 measurements do I need? Which dimensions do I need?
Multiplication.
Okay, that's a math operation, so I am going to write that down because that's part of it. What dimensions, which measure do I need?
Centimeters.
Okay, so that's the unit. And it's going to be squared. But what part do I have to measure on the face?
Like how long the corners and the sides are.
I remember doing this.
And do we call that length and width?
Yes.
All right, so just to make the picture on your book remind us of something that we've had before, I'm going to ask you, look at this one in A. Look at that face in A. And that, if you can think of it, is like that. Does that ring a bell? Do you remember doing length times width? It's kind of like an array, isn't it?
Yes.
What is the surface area of this rectangle?
Oh, that rectangle is 1, 2, 3, 4, like 3 and 3.
3 and 3?
3 and 3.
3 times
3 times 3? You started doing a different strategy before. I heard you.
Yeah, I did this and I already.
Okay. I'm glad you did an I ready. But you started to count all of them, right? And what did you get?
6, 9. I got
9. Do we get the same if we do 3 times 3 is 9?
Yeah.
All right. Now we have to look and see for abstraction, what is the problem asking me to do? Well, first I have to, it says compare, but can I compare them as my first step, or do I need to do something before I compare?
You need to do something
before you compare.
And what is that?
Compare.
Answer or like.
I love that you said brainstorm, except brainstorm is good for thinking of which strategy we would use, or it's good in writing, but what about how can we compare the surface areas of the boxes? Does it give us the surface areas of the boxes?
No.
So,
Yes.
I think we should focus on the information it gives us and turn that into surface area of the boxes. Is that something that you could do?
I think so.
You think so? I'm good. That's a good attitude to have. So you are going to look at what the problem's asking you to do to find surface area. Look at information you should focus on, which we identified. What information are we focusing on from the diagram?
Length and
Length and width.
Width and length.
Do we need to focus on this information that we are multiplying?
Yes. Big brains.
Do we need to focus on how many parts there are to the net?
Yes.
Maybe. Wait, no. Wait, yes.
Yes.
Maybe. Maybe
no,
possible.
maybe.
It's going to ask us which box will use the least cardboard. So do we have to know what it is all together?
Yes.
Yes.
Because if we don't know all of them, are we going to know how much cardboard we need to make the box? No. So when we look at it, that is an important piece of information. And this diagram, these are great diagrams. If you work on C, who can work on A or B? Okay, A or B? A. You've got A, you've got C, and do you want to work with C or with me? With me? All right. This is what you're going to use as you diagram or use these pictures to show us how you figured it out. And then I want everybody else listening to the other people's strategies in case they need some input, some feedback. Maybe there's some things we have questions on. Let's get started with this. The first thing is maybe you can explain what you thought you had to do. So the first bubble is, what is the problem asking me to do? So maybe you can start with that one. Sounds good? Oh, I can't hear you because my ears are old. They're clean, but they're old.
I can.
We thought they had to like multiply them like 3 times 7, and they would get the answer. But it was right.
But then you changed your mind? Yeah. Okay, so where did you, when you were looking for important information, where did you get 3 as an important piece of information? Okay, so you see lots of 3s on the boxes. Do you agree that 3 is an important piece of information for this? Okay, now I'm curious about the 7. Where did you get the idea of 7 being important information?
Because I have these 2 boxes,
Uh-huh.
and I have got the 4 from right here, and I have 3, and I got 7.
Okay, so I heard you say that adding. Yes? If we look at abstraction and we look at what might be an important piece of information and what it's asking you to do, remember what we came up with as far as asking us to do? What is it asking us to do? When we want to find surface area, what are we asked to do? Multiply. So one of the important things is when you use abstraction, go back to our initial notes, because we have the question, what information should I focus on? But you also want to make sure to check and see if we pointed out that information. So if the information says we're finding area by multiplying, you can always go back to your original notes. It's a really good idea to take these questions that you've asked in your head and write down on your paper in case you forget. That's why you have notes. None of this is a test. Does that make sense?
Yes.
Okay, good. So is there a way you would change your ideas? And this is where you could write on the board with the notes instead of, instead of adding all the 3s together, how could you find, or do you know how you could find the surface area of one of those faces? Oh, I can't hear you, and you know what? If you're going to need a lifeline, they need to hear you too. And you can ask them.
Oh, no.
No, we don't. So how many faces do we have that are 9 square centimeters?
3.
Well, if I look at this tissue box, I have top and bottom, front and back, side and side. How many is that?
4, 6. No, 6, 8.
6 faces. That net has how many faces?
6.
What's the square, the area in square centimeters of each face?
9. 3.
I'm hearing different information. I heard 3 times 3. It's so hard for me not to want to write on that with my marker. So let me erase this for a second. I've got 9 of those faces. Wait, how many of those faces do I have?
6.
This is my sloppy cube. We know there's one in the back and one in the bottom. And each of these is 9 centimeters squared. How many faces do I have?
6. No, 18.
How many? So I'm going to build a box. I say, Daniel, help me out. Every time I ask for one, you give me one of these. That's going to be my face. I need a face for the bottom. I need a face for the top. I need a face for the sides. I need a face for the front and the back. We're going to pretend that these are 9 square centimeters. Are y'all ready?
Yes.
Okay, with me. Count with me. 9.
9.
18.
18.
27.
36.
We're falling down here. 45
45.
and 54.
54.
So what is the surface area of that? 54 square centimeters. So if using the diagram doesn't help you get all the information, can you start using other tools besides just a picture? Because all this is a picture that is, I can touch it and move it around.
Yes.
Does that work?
Mm-hmm.
All right, excellent job. Do you have any questions?
No.
Anything to say?
No.
You think you learned?
Yeah.
All right, excellent. Do we want to do another one? Using these tips and questions, how could those help you when you've got so many numbers on one board? Because I know when I look at this, I just say, oh, it's a lot of numbers. How can I use this to make it more comfortable and feel more confident? Nevaeh?
You can break it down.
You can break it down. Oh, and that's also another strategy we're going to talk about. Maybe tomorrow. Yes?
You can think what this problem is asking me to do.
What is this problem asking me to do? Excellent. Because it's right there. And when it says, what information should I focus on? That's really important because we saw it was important in the last story we had. I'm going to show you how this is really important. You can see this, right? What if I show you this? I don't need that extra 3. I don't really need any of these other ones because they're all the same. When I'm in here, I don't necessarily need to use all of these numbers. I can use these numbers, but I don't need that. If I use these numbers, I don't need that. Does that make sense to you?
Yes.
There are many more numbers in here than you need. So if you focus on the information that you need, it might be easier for you to actually eliminate information that they just throw in to test and confuse you. Do you think this would be easier to do without the diagram?
No.
If they just wrote down what the measurements were?
No.
No? So the diagram and the picture really does help show the important information?
Yes.
One last question. Did it show only important information?
No.
No, so you have to circle back to this step to make sure that you really are sorting that information out. All right? And I'm going to tell you this. Out of all of the strategies, abstraction is really something you use a lot in reading and also in real life too, where you have to look at a situation and say, what do I really need here? And how can I work with it? This way? I got to do this again because it's a little confusing, which is fine. Or, well, we really need to do this 10 more times. It's okay, whatever you do. All right, excellent. I'm very proud of you. So, do you think that we can use the nets to find the surface area of these figures by using abstraction?
Yes.
Yes.
And do you think we should practice a little bit more because it's a good strategy?
Yes.
All right, then you did your job for the morning.
As you plan to frame, prompt, and highlight computational thinking within your lessons, consider the following questions. What are some strategies my students could use to solve the problems in this lesson? How might a CT strategy already be part of or add to those strategies? How might I recognize when I see my students using a CT strategy? How might I identify when it would be helpful to prompt a student to use CT?